Welcome everybody to the 17th Annual Research Day at the Eugene Applebaum College of Pharmacy and Health Sciences. Thank you all very much for joining us. 2020 is a year that has brought us all unprecedented challenges that have really asked a lot of all of our personal and professional efforts. It continues to be important, however, to showcase all the good things that are happening at the college, including research. And our students and faculty lead so much and participate in so much at the college. Today is a day their hard work is going to be celebrated, although virtually, definitely celebrated. Research is an important part of our mission, and it's an important part of each day here at the college. And while we won't be walking through the commons, putting our hands on the posters like previous years, I hope you have taken the opportunity to view the abstract book and the student videos that have been posted online. Earlier today, I was told that the YouTube videos have over 1,100 views already, and I'm sure some of you haven't seen them all yet. So we're off to a terrific start. As always, I'm immensely proud of the work that happens in this building, and I'm proud of our students and faculty for all of their scholarship and commitment to health research and good health. At this time, I want to thank the Research and Grants Committee very much for their time. Diane Adamo, Paul Kilgore, Malcolm Cutchin, your work has been full and daily, and we're just delighted that you've had the energy and great creativity to bring this to all of us today. I must add as well that people behind the scenes have had a significant hand in all of this. So a terrific tip of the hat to Tiffany Cosmano, Marissa also, of course, and Michelle for all of your work to bring this to us today. Finally, I'm thrilled that our speaker, Dr. James Thomas, has made the time to share his terrific work with us. I know we will all take something away from his very exciting presentation that is in one moment. I saved the introduction for Dr. Maher, but I want to say my personal thanks and appreciation to Dr. Thomas for joining, and for all of you for listening in. So with that, Dr. Adamo, I'm going to turn it over to you just to brief everyone on the housekeeping rules, and then we're set for a very exciting talk. Diane.
Thank you. Thank you very much, Dean Lysak, for that welcome. And welcome to all of those of you who are here today. We really appreciate you joining us. To help make this virtual event more engaging and a success for all participants, let's try to stick to the following housekeeping tips. Number one, please enter your full name as your screen name. This helps us identify who is asking a question. This also helps us to identify the award recipients. Number two, please keep your mics muted to avoid any unexpected background noise. Number three, if you are comfortable, please turn on your cameras. We would love to see our audience. Number four, if during Dr. Thomas's presentation, you have a question, just click the raise your hand icon and you will be called upon to unmute your mic and ask your question. If you are unable to unmute your mic due to background noise, please submit your question via chat and we will facilitate your questions. We're also scanning our audience regularly to see if any little hands pop up. Dr. Thomas has made it very clear to us that he wants us to be an engaging and active participation and presentation. So we've got the go-ahead to be asking questions and raising our hands and questioning all the wonderful things that we are about to hear. We welcome you and we look forward to your input. Now I'm going to hand it over to Dr. Maher, Chair of the Department of Healthcare Sciences and Associate Professor, for our introduction.
Good morning, everyone. I'm so excited to see so many people participating in Research Day today. I have the distinct honor of welcoming our invited guest, Dr. James Thomas, whose work I was introduced to through a colleague at the Virginia Commonwealth University. Dr. Thomas has been a licensed physical therapist for 35 years, with over 15 years clinical experience treating patients with complex orthopedic and neurological impairments. He has extensive experience in managing projects that require complex integration of kinematic, kinetic, and electromyographic data collection techniques. He uses this to assess trunk biomechanics during volitional and reflex tasks. At Ohio University, he developed a national recognized motor control laboratory and tested more than 400 participants with subacute and chronic low back pain. He joined Virginia Commonwealth University in August of 2018 and established a state-of-the-art motor control laboratory in the Department of Physical Therapy. The primary focus of these labs is on development and testing of novel virtual reality tools for assessment and treatment of patients with disabilities which arise from pain, balance disorders, and poor trunk control, both due to neurological disorders such as Parkinson's disease. Dr. Thomas's motor control laboratories have been continuously funded since 2004, with the majority of his support coming from the National Institutes of Health. He publishes his work in prestigious journals such as Spine, Journal of Neurophysiology and Pain, and he regularly serves as a grant reviewer for a number of NIH study section panels. Currently, he is a principal investigator on an ongoing NIH-funded phase 2 randomized clinical trial, VIGOR, Virtual Immersive Gaming to optimize low back pain recovery. This examines the efficacy of an immersive gaming intervention to reduce kinesiophobia and to improve motion in participants with chronic low back pain. I now turn it over to our well-introduced guest and well-valued Dr. James Thomas. Welcome.
Thank you. Thank you very much, Sarah. It is really a pleasure to be here. I am going to now try to share my screen and see if I can get one other thing set here so we can be on our way. And I really am looking forward to doing today's talk. I got one last thing here and it's already clicked. Beautiful. Okay. Yeah, so I have been doing VR work for about 10 years now and have spent quite a bit of time trying to understand human control of movement from a perspective of understanding trunk control and how various impairments, both orthopedic and neurologic, will impair trunk control, and particularly how various fear cognitions can influence behavior. So what I'm hoping that today, out of today's talk, that you will get an understanding of some of the work I'm doing, some of the potential promise from virtual reality, and get a sense of how these things are developed. As stated, I am happy to keep things moving and interact with anybody along the way if questions arise. So with no further ado, we'll start our talk here.
Research is about trials and sometimes errors. At a top-tier research university, you learn to manage both. Practice makes perfect, but research makes possible.
That's probably a optimal sentiment for today's day of research at Wayne State. And as we move forward, we are really engaged in trying to understanding human behavior. So today's talk, I'm going to be going on how we harness the power of VR for rehabilitation. I plan on discussing how we develop a VR intervention, some results from recent studies that we've completed on our virtual dodgeball, and present a case study in VR development, how you go from beginning to finished product. And hopefully as we get through this, you will gain an appreciation for how this work is done and where you may take the work that I presented here and now take it to the next level in your own laboratories. So first, when we talk about virtual reality, the most important thing is what is the level of immersion? So if you think about it, watching something on a flat screen TV that's not immersive, a 3D TV is semi-immersive, and the head-mounted displays are considered fully immersive. this all has to do with how much agency or presence the person feels. And this is really an interesting construct, because the more the person believes that they are within the game space, the more that they can engage in whatever the target behavior is. So the level of immersion is really an important consideration in developing VR. Is distraction an integral component for interventions, such as, if I have an individual with severe pain, and that was like some of the earliest work on wound debridement. They would have, with children, they would have them playing video games to avoid the pain associated with this. So distraction is a component, and you want people to sort of leave their body and believe that, oh, I can do this, and we get an implicit learning strategy that we can develop. How we present the avatar actually matters. So are you presenting the avatar in a first versus third person perspective? So on the screen here, this is a first person, right? You can see your arm in front of you, but that's, if you're reaching out for a target, that's all you would see. Conversely, in a third person perspective, you're actually seeing the full avatar, and you're now having to control that avatar by watching how it moves. It's a little bit of a separation. Well, one of the things that we found is that it does have an effect on motor performance, and specifically that if you're watching or you're playing a game in the first person perspective versus the third, you actually move more. And it's subtle here, but you can see that at the spine and at the knees, these individuals playing the same game played it differently when their avatar was presented in the first versus third person perspective. That matters, especially if you're trying to get some target behavior. I want them to move in a certain way. So understanding how you present the avatar is an important consideration when you're developing an intervention. So fidelity to the real world is another aspect. So spatial fidelity. Does VR space map accurately to the real world? In most of the work that we do, we have it down to millimeter mapping of VR space to real world, because what I want is when they take that headset off, whatever behaviors we have developed while the headset is on, it doesn't extinguish. So we want to have that. However, there are times when you want to actually distort the VR space to enhance the treatment goal. And one could imagine somebody with a cerebral vascular accident and left-sided neglect. And what can happen here is they're not even addressing the left side of their whole workspace. So we distort the visual field to get them to engage that part of the body, which they're not even recognizing. And hopefully through that, getting some collateral sprouting and getting some neurophysiologic changes to improve function. Temporal fidelity. So this is a really big thing in gameplay, is that if the game doesn't match your movements or is delayed, one, it doesn't feel right, and two, it can actually induce a level of nausea. But that being said, real time does not exist. There's always going to be probably a 10 to 30 millisecond delay, because you have to map 2 points of the body and where it's going in time and then translate into the space. The one thing about temporal fidelity and aligning this is an interesting little factoid, is that if anyone's ever been on a ride at Disney World and you go through the Magic Mountain, what Disney does on purpose, their engineers, is they offset the visual display by about a frame or two from the motion of the car you're in. And they realize that just offsetting it 1 or 2 frames will make most people a little bit nauseous. And they feel they got their money's worth, that they come off the ride feeling a little queasy. And then and the other thing you notice is when you first come off the ride, you get a blast of cold air right to the face. That's also designed to kind of reset your vestibular-ocular system back to it. Now, again, that's for most people, but can you imagine the research when they were trying to decide how many frames? Okay, whose turn is it to go up? 3 frames? Nope, that's a problem. Clean up on aisle 4. So it's really a fascinating aspect when you think about how some of this is developed. But the temporal fidelity does matter. Any inherent latency, you have to figure out, is that going to have a negative impact on your treatment goals? Okay, so those are some of the important aspects. Now we start talking about game development. Well, game development is an iterative process. And I like to call it the Goldilocks phenomenon. If I make a game too easy, the patients will get bored and will not engage in target behavior. If the game is too difficult, they get frustrated and don't engage in the target behavior. What you're trying to find is that, that the Candy Crush type of game where people want to play it, right? As clinicians, you want, presumably, you know the target behavior you want them to engage in, and you want to engage at a certain level. So that in development of these, I say games, but really in this talk, games are synonymous with treatment. So what are the first steps? You need to collect the critical background information. This is what's going to inform the decision-making process in your intervention. What are the goals of the intervention? Do you want to have them to move more? Do you want them to move less? Do you want them to move in a certain way within the workspace? Well, a considerable amount of my work has been looking at the fear avoidance model of low back pain. This was developed by Leyen in 2000. And this is basically saying if you have some sort of injury and then you have pain, depending on your underlying level of catastrophizing, so this is that you're always worried about what's going to happen. If you're high in catastrophizing, you're going to get into this fear of movement, avoidance, and disuse disability, and you kind of sit in this circle. Conversely, if you have low catastrophizing, you engage in movement and you recover. So what we ended up doing was really avoiding, okay, we're bouncing a little bit, there we go, avoidance and hypervigilance. And we wanted to know, okay, well, what exactly are they avoiding? So we did the initial studies that have mapped fear cognitions to motor behavior in low back pain. All of this starts, and this figure I'm going to pop up several times. This is based on a standardized reaching test. So if you have your hip height, your trunk length, and your arm length, and we say, all right, how much do you bend? If you bend 15 degrees here, where would this target be? So we have this idea of the normalized pattern. We have hip height, trunk length, and arm length, such that if you were to bend 15 degrees, this is where your arm would be, 30, 60. Now, nobody moves like this. As a matter of fact, this movement here at 60 degrees is we would tip over, we would fall down. But what it does is allows me to compare movements or place targets for people to reach at, whether they're 6'5" or 5'5". So that is an underlying theme to all my work, both in real world and virtual. So our early paper on pain-related fear associated with avoidance of spinal motion during recovery. So we looked at 44 participants, 3 weeks out from back pain. They reached for 3 targets. We measured their 3D motion characteristics, and we also looked at their pain and their scores on the Tampa scale for kinesiophobia. And what we found here was pretty amazing. If you look here, what we have is reaches for the high target, middle, and low. And at each of these, when we separated out our cohort by high versus low fear, is that the individuals with high fear move less than the individuals with low fear. And the interesting part, it wasn't because they lacked the motion, because you say here, this is 30 degrees of spine motion. Back at a high target where they only needed to move about 10 degrees, they still move less. So individuals with high fear avoid motion of the spine. And we think that that's what leads them to have chronicity. We've also shown this in individuals who have recovered from an episode of low back pain, that increased fear has decreased lumbar angular velocity and acceleration. Increased fear in experimental back pain leads to decreases of lumbar flexion. And in chronic pain, increased fear has decreased lumbar flexion and decreased activation of the erector spinae. So fear avoidance, individuals with back pain and high fear do not want to move their spine. That is the genesis, or that was the underlying construct of what we were trying to attack with virtual dodgeball. We wanted a video game that could promote lumbar motion in individuals with chronic back pain and high levels of fear avoidance. We want to use an implicit learning strategy. So the advantage of this virtual dodgeball, it allows for dynamic lumbar flexion. We can customize it to each individual based on their initial assessments. We can scale the game across visits, and we can provide a fun distraction while encouraging movement. So we did the learning study. This was a phase 1 clinical trial, and it's lumbar excursion activities reinforced novel interactive gaming. So again, the acronyms are always fun with the clinical trials. This is our very first version of dodgeball. And a couple things you should note about this is the opposing players aren't moving when they launch the ball, so we had to put a light in there to give the player a heads up. The fans are all just two-dimensional, and the player here is playing on a 3D TV with shutter goggles, so it's a very early version of our development. So this led to a publication in Journal of Pain, Feasibility and Safety of Virtual Reality Dodgeball. This was our randomized trial. And what did we find? Lumbar flexion increased within and across gameplay sessions with strong positive endorsement of the game with no increases in medication, pain, disability, or adverse events. However, this was only a 3-day intervention because it was a safety trial. So to get larger clinical outcomes, we need longer than a 3-day intervention, which anyone who's ever treated anyone with back pain would say, well, yeah, of course you're going to need more than 3 days. So that led to our current trial is a phase 2 randomized clinical trial. And this is the bigger study, virtual immersive gaming to optimize recovery in low back pain. So we've been racing along with this. We need 230 participants with chronic back pain. There's a 9-week intervention and almost a 1-year follow-up, upwards of 48 weeks. So we were sort of racing along with this up until the university closed March 17th because of COVID. So we ended up dropping, we lost 30 subjects that we had to drop who were on protocol, and then we were closed for 3 months. So this is going to be interesting to see how we recover from this. We've calculated we need 8 months to fully recover our recruitment. We're just going back to the NIH to discuss how to recover. But every clinical trial in the country has gone through this with the shutdowns due to COVID. But our lab is back up and running. We've been back up and running since July 10th, and we're almost back up to full speed with recruitment. So hopefully at this point, we're just going to keep rolling through this. So I want to now kind of talk about the development of the VR, sort of a case study. And this time let's start taking a look under the hood of the steps and how we do this. So again, back to the standardized reaching test is that if I know that I have a point in space that I can normalize to different people because based on their hip height, trunk length, and arm length, I can say what virtual events do I want to have happen in this area of the workspace. I can also do something where I set up a reaching task and have somebody move and say how much are they willing to move the spine, and then use that to adjust when their spine is moving, where are they in space, and use that as an initial go point for our virtual reality interventions. Either way, what we're doing is we're customizing each intervention specifically to the patient. It is absolutely tailored medicine. So we start here with, okay, well, this is where we want the virtual event to occur. And in dodgeball, well, we're going to be launching from the opposing player, and we know the distance, we know the height, and we know the height where we want this to be intercepted. So we create this trajectory, our launch point, and our intended interception point, because people being what they are, they do things in a variety of ways. So to calculate this, we take our input variables of intended interception height, our distance to interception, our launch height for the virtual reality, our virtual object, and what is our initial velocity. Once we know all those, then we can calculate what the launch angle is through sort of standard equations of motion, and then we can say, all right, now we know that ball is going to go on a parabolic flight, and the patient can intercept it by bending at a certain degree. Now, what you'll see here is this is our next generation of dodgeball. The player's delivering it, and you can see we're doing a green screen here. So this is a participant playing, and he's bending to intercept the balls that are launched by the virtual players using that simple set of equations. Once we know how far the player is, where they're going to launch, where we want the ball to end up, and then we look for interceptions. The player scores points by blocking. He loses points by getting hit with the ball. So those are some of the parameters we put into our game sets. So that was how we started. That was dodgeball. But what if we get beyond dodgeball and we said, well, we want to create a whole suite. And we want to have a suite of games that include both assessment and treatment modules. And we want the treatment modules to allow for a gradual increase in difficulty of the game or for movements. So in this case, we have our mover assessment model called Reachality. This assesses current levels of movement-related fear, as well as assesses spine motion using my standardized reaching task. So here you have a participant. He'll get some instructions that'll come up on the screen that'll tell him how to play the game. He'll say it's okay. A target will appear right here, and then a question, how much pain do you expect? And he'll rank that. And then we'll ask him, how much fear do you expect or harm with doing this task? Once we get that, then we'll reach for the target. This is obviously a high target. He's reaching with the right hand, and we can vary all these parameters. So now this is a low target, reaching for the left hand, right hand. We can do it with both. And we have simple text files that we can use, and we can share this. We actually have a group at the University of Florida that I'm collaborating with just completed this, looking at the cortical response to the reaching task and fear. And that paper is coming out and just got accepted to the Journal of Physiology. So we'll have some fun stuff. But the VR allows us to create any type of environment and to precisely put these targets where we need them to be, and in real time assess what's their fear of pain and fear of harm, which we then input right into our data stream. So the mover suite are treatment modules. We have matchality. So matchality is a bit like the old game Simon, where you had the 4 lighted cubes you would reach out and touch. In this case, we're using a 4x4 set of cubes. We'll show in just a moment. But the player is reaching to static targets at a self-selected pace, a rather low-level game in terms of physical requirements. Then we have fishality. In this case, the player is going to net virtual fish to jump out of a lake. In this case, the fish are on high parabolic flight. They're gliding up, and you can time your reach and get to the net fairly easily. And then we have dodgeality, which is our dodgeball game. And in this case, the player is going to intercept or duck virtual dodgeballs that are launched at them. And again, in dodgeality across this, we can actually increase the difficulty of the game by changing the initial velocities. And so that the ball, as you're getting better, will launch the balls at a higher velocity to get you to move faster. So once you're able to engage in the workspace, are you willing to move quickly and generate the necessary torque to do so? So here's matchality. Again, we have 4 rows, a 4x4 set. Requires 15, 30, 45, and 60 degrees of flexion based on our standardized reach task. And you can see that the player is going to reach, and he'll have to think about this and do it in the order the cubes light, just like the game of Simon. So there's a level of concentration. This can also be used for individuals with cognitive impairments. Now, the thing to watch here So if you notice there, the cubes break, and they break as you would expect, because once a glass broke, you'd expect it to fall down. This goes to our aspects of immersion and fidelity. So now in the next level of this game, they're playing on a low Earth orbit. And so when the cube breaks, we have it behave as it would with the gravitational field, that is, if you were in low Earth orbit. These are little touches, but they're things that if it basically dropped down in front of you, wait a second, it doesn't make sense. I am in space, something different should happen. So we try to do this to facilitate greater immersion. We also do this to provide greater levels of variability and changes within the game so they don't get bored. Remember back to the Goldilocks phenomenon, if they're playing the game, once they get it, if they're bored, they don't want to do the game. So we want them to engage, so we change scenes. So fishality, as I described before, is there's launches along high parabolic flights. And we know where the fish launched, we know what our interception point is, but now we're going to choose what height do we want for the parabolic flight. If we want them to move quickly, we may have a very low parabolic flight. If we want them a lot of time, we'll make an adjustment and make that a wee bit higher. So again, our input variables here are intended interception height, distance, launch height, but then the height of the parabolic flight that we desire. And then we have to calculate what is our initial launch angle and what is our launch velocity to achieve our input variables to solve those equations. Once again, here's from the player's perspective, or actually external watching the player. And people really like this game. It's very peaceful. It's on a nice lake. It's well done. And every time he catches a fish, he puts it in the tank, he gets more points. And there'll be something in just a moment after this next fish. Oh. So we also have sharks come in, which is somewhat different. You don't expect those on a lake. And this is one more to tie back to dodgeball, the idea of having the duck. So it also keeps people surprised. It creates elements within the game space where they're not thinking about themselves. They're just engaging in this nice game. And then all of a sudden the shark's jumping out towards their head and they have to duck. It's all designed to encourage motion in individuals trying to avoid it. Interestingly enough, what we're finding is that while these games were initially designed for, so this is one of our sort of game things that go on, make the programmers play around and try to make the games crazy. But when we did the games, we're trying to have stuff for people with trunk control. We initially did it for back pain. However, these games are easily applicable to individuals with a variety of neurologic disorders. And in fact, we've got preliminary data. We're working with this suite for individuals with Parkinson's disease, because it turns out that trunk stiffness and trunk control are really problematic in individuals with Parkinson's disease. And the medications, while particularly good at dealing with appendicular muscles, they're not very good at addressing stiffness in the trunk. So we're trying to use this to try to facilitate function. Now, what you've seen up here in this dodgeball, if you've seen a variety of scenes that we have had here, we went from standard, and I'm going to take 1 second to spin back through this. Let's see, I'm going to wait till this finishes up. Let's see, I'm going to play this one more time, just to kind of show I was over talking this one. So this is our easiest level of dodgeball. We call it cannon dodgeball. It uses the same idea of fishality, high parabolic flight. The person can get to the ball easy. You know, if you're really sore, you don't want to move fast. So we want to start them off gently before we start really working them into a more intense motion. Then here's our standard dodgeball. And then as they get better at this, we then will change the scene to night dodgeball. And again, it's the idea of visual cues and trying to pick up on where the ball is in space. I have to move a little faster, and it keeps me engaged. And then finally, space dodgeball is where the perception is, because of the changes in gravitational elements that we put into our equations, that the ball appears to be moving faster, and so they have to go at higher velocities in this. So it's a gradual progression of graded exercise for these participants. So now, what is our next generation, and where are we going with this? Well, BuildABot. So this allows a clinician researcher to adjust a variety of game settings to encourage specific movement patterns. And it really has wonderful ways that people can twist, bend, reach. There's a variety of elements within this. What was our inspiration for BuildABot? Well, for anyone under the age of 50, you may not have heard of I Love Lucy or seen the Chocolate Factory episode. This is probably worth the price of admission to this talk today.
All right, girls. Now, this is your last chance. If one piece of candy gets past you and into the packing room unwrapped, you're fired.
Yes, ma'am.
Oh!
So this is easier. Yeah, we got... Listen, Ethel, I think this...
that was my inspiration for BuildABot, which you'll see as we go to the next, is that it's a series of conveyor belts, and parts come off, and the person has to build robots. And the robots have different tasks, and they have to align all the colors and put together the bot. There's 3 parts. The reference frame here, we can put at any height. We can change the heights of the belts. We can also change the speed of the belts. So I could have recreated the iconic I Love Lucy scene. And all of these, as the individual gets better, there's a variety of gaming environments. This young woman who came into my lab last year and developed this is quite a brilliant programmer. And it's a wonderful little game that allows us the experimenter has incredible flexibility. And you can see my postdoc was very happy about being successful with building a robot. And then there's all kinds of underlying game elements in terms of the robots. You can build a fireman robot, a policeman robot. They go around, there's mischief robots, all kinds of things emerge. But we can adjust so many settings in this game that I can actually modify it for a variety of disabilities, not just trunk pain. And in fact, we've actually submitted a grant application today to look at individuals with fibromyalgia and use this as the intervention because of our ability to scale. Fibromyalgia has a variety of disorders that are not simply located to the spine. And BuildABot, we actually have a whole suite within this. We're only presenting this part of it today, but it's really a wonderful game that was developed by this, again, this young woman programmer who is at NYU getting her PhD. It's Megan Charity. She is, I keep waiting to see her name in lights. She was so incredible. So that is our BuildABot. So behind the curtain, how do we do all the filming that you've seen? Well, we pull up green screens within my lab. We have this piece as part of our virtual reality system. It's one of our tracking pucks of the Vive. We put this on top of a camera. So now we would know where the camera is relative to the headset. And then this gets fed in, and my lead programmer here, Matthew Iteration, pulls all this together and put this to, so you could actually see what the motion is behind each of these games. So in conclusion, VR has the potential to fundamentally transform rehabilitation, delivery of rehabilitation treatments. And particularly so, you know, when people are having hard times coming in. I said before, we're doing work with Parkinson's disease. We have a group we're working with. We're actually trying to make a mobile version of the Mover Suite, a multi-person version of the Mover Suite, so individuals with Parkinson's disease can actually play at home against other individuals in the community with Parkinson's disease too, and especially now in trying times where they can't get out, they're at higher risk. So there's some really interesting development things that can go with this. As the technology rapidly evolves, these treatments can easily be customized for each patient. So again, I imagine in 5 years, you know, most of this is going to be presented on very inexpensive computers and very small headsets. There's some really interesting stuff in assistive or augmented reality headsets as well as virtual reality. You really have to have a sound neurophysiologic rationale before using the VR. I mean, have a reason why. What's the science behind the intervention? I think you'll go far if you can develop that. And lastly, I'd like to thank my lab team, a combination of kinesiology students, engineers, PTs, postdoctoral fellows, a really fantastic team where none of this work is possible without all the incredibly heavy lifting by this entire crew. They're all very happy and lucky to have them on working for me. And then my collaborators at VCU, my postdoctoral fellows, Dr. Vanderveen, Dr. Spenkovic, and Dr. Peoples. They're truly fantastic. My colleagues at Ohio University, South Florida, University of Florida, and Northwestern. And of course, I wouldn't be here without the funding sources from the National Institutes of Health, the Osteopathic Heritage Foundation, American Osteopathic Heritage, Osteopathic Association. Then finally, a big thank you for inviting me. I've really enjoyed the great honor of speaking to you today. And now I'm more than happy to take any questions you may have about my work. Thank you.
I have a question.
Brilliant.
Dr. Thomas?
Yes.
So I find your whole presentation so interesting. I'm so intrigued by everything you just presented. A lot of the patients that you have were standing. Have you done any work with anyone that's in a wheelchair?
That's a great question. One of the things that we're doing, I was giving a talk at, they're doing a new rehabilitation hospital. There was a fundraiser I was talking at. And we're engaging with individuals with spinal cord injury to try, because I think this game can be absolutely adapted. We've actually modified it in terms of, it can be played seated, not only for individual, well, not even just with spinal cord, but anyone who is wheelchair bound, but you want them to have the ability for trunk control. My whole task can be normalized to, you can set the hip height as where they are and where it is relative to their hip in the chair, and then everything else would play the same. So yes, we are actually looking. So one of the young women that at this talk was in a wheelchair, and she's actually a rower. She was a collegiate rower before her accident. She still goes on the rowing ergs. And so she's going to be coming down to our lab to help us develop, try to get community feedback. But yes, there's some really interesting work. There's also a colleague of mine who actually did my, was a PhD student of mine way back in the day at OU, is now on faculty here, who does some work with spinal cord injury and doing some work with arm movement, in which they, in the VR, they move their arms and it replicates like their leg is moving, like they're walking, and it has interesting effects on reducing pain. It's a really fascinating phenomenon.
Well, one of the reasons why I asked also was I have an uncle who's, well, he passed away since, but he's a paraplegic from an accident. And just getting any kind of movement, you know, was a challenge. I mean, when he was younger, he was involved in like maybe a paraplegic basketball game. But as he got older, any kind of movement, he didn't have access to, and sometimes he couldn't even leave the house with weather permitting and things like that. So I think a game like this would not only be like so stimulating for somebody mentally, but also helping them just to stay in shape, because, you know, the lack of movement just in doing, you know, anything from the waist down, but just physically with your arms would really be something wonderful, I think.
Yeah, there's some really interesting work, and I don't have it on this, actually. Okay, so this is using Fishality for balance.
Catch the fish.
And this is my mother, and that is my father. He's 90 and she's 86 at this time. But she's having cognitive decline, but we're working on, I was doing a talk in Boston and I brought my system with her. So that was the shark. I'm really a bad son. I didn't tell her about the shark jumping over, scared the living daylights out of her. But the reality is that a 90-year-old and an 86-year-old can engage in this. And I think, again, they could still stand, but when my dad was, after his hip replacement, was in the wheelchair for a while, yeah, we used this game to try to get them to engage in the process. So I'm looking to do more and more with that next generation. And some of my postdocs have, one of my postdocs has, her background is in spinal cord and stroke rehab and such. So our next gen are going to be specific towards that population.
Thank you. Very fascinating. I find the whole work fascinating, even for maybe developing even for classrooms for kids that are younger, just to get them, they love video games, and just to get them more active in life in general. The whole avenue can be explored.
Our next big thing is multiplayer, trying to get people playing against each other within the cloud based on how they move. So my programmer and I are working on some details on how we develop that.
I had a quick question.
Yes.
Hi, I'm Erin. I'm a graduate student here at
Hello, Erin.
Nice to meet you. An excellent talk. It was very enjoyable, very interesting work. And I was wondering, particularly within the context of persons with neurologic disorders, you do such a nice job of individualizing a variety of trajectories and target locations within your paradigm. And I was wondering if, when considering someone with perhaps cognitive deficit, would you consider individualizing these paradigms based on perhaps like baseline processing speed? Is that something that you guys are thinking about, or would you not think that that would have an impact? Or
Sure. I mean, I think that's a great question, and the element on how you adapt to their ability to process is, so in some ways that is inherent in some of the things. So like in dodgeball, physics being what they are, is we have, unless we make some adjustments, we have to launch the ball until we went to the sort of parabolic flight, the high parabolic flight. We have to launch the ball at a specific speed to cross the distance. The math is what it is. Otherwise, it's just not going to make it.
Mhm.
But with parabolic flight, you can slow the games down, and then you can try to do some things. There's really some interesting stuff we're working on too, on the idea of with balance disorders and how they're processing. You can deal with the idea of what is happening with the lateral optic flow to change, to help reset the vestibular ocular. In terms of cognitive processing, what might be interesting as I think about it, we have another game similar to Matchality. We have a game that we call, this is our cognitive trainer, and I'm just going to bring this up just real quick. So what we have here is a game of concentration, which you can sit there and slow the game down and just have a variety of cards and figure out what is their level of processing. And you can sit there and go, are they having shape issues, shape recognition? The cards, these are just the classic, what we used to call the game of concentration growing up. But we can do a variety of methods on that. We could do this. And this is also one that could just as easily be done in a seated posture. This is an early Vegas cheesy version of the game, but these are some things that we can do. So VR really gives you amazing abilities to modify and change your task to whatever. So it is interesting with the cognitive declines.
Yeah, very interesting. Thank you.
You're welcome.
I had a quick question about the dodgeball game.
Yes.
So it looked like they were hinging at their hips. Were they specifically instructed? Like if a ball was coming at me, I might squat, but it looked like they were really hinging at the hips.
So that's a really great, so great question. Two things. One, and I think most of the people on the dodgeball, I think, I gotta look who my folks were. I think I had mostly female grad students who are gonna tend to move more from the hip than the spine, at least from most of the work that I've seen. There's no instruction in how to move. And now the game, so the instructions of the game, the way it's scored is the ball is launched and you have to, if it's a normal green ball, the only way you got to point is by, it's coming at you. You have to block it with the virtual ball in your hand, okay? Alternatively, if it's a black ball and you hear a duck quacking, then you can't block it. You're instructed to duck. But you're not told, or you can sidestep, you can move out of the way. But the idea is that people are going to move the way that they want to. We're not instructing anything. In this case, what I'm really trying to do is get people to not think about moving and to use this idea of the competitive game environment to get them to engage in areas of the workspace that they've really avoided because of fear cognitions, and that through an implicit learning strategy over time that we're going to get changes in their motor programming so that they re-engage in those spaces and are then less susceptible to recurrence and chronic pain. But we're not giving them instruction. That was most likely just the unique characteristics of the individual. And I believe it was mainly young women, except for who we had doing the task. And they'll tend to move a little bit differently.
Okay, thank you.
You're welcome. So this is normal. I can normally see the whole audience and see who's still curious. This is the great challenge of Zoom. I see 4 or 5 faces. So if you have any questions, anything at all, glad to answer them.
I have a quick question.
Sure.
Hi, my name's Anthony. I'm a final year PT student at Wayne. So
exciting.
We talked about a little bit in the talk about chronic low back pain and getting people to move and avoiding or trying to challenge the fear avoidance behaviors. Have you looked at how VR and your research has compared to other strategies to attempt to do that? So, I know there's biofeedback units, there's certain like cognitive behavior therapies that have been used. How does this compare and where does it sort of line up, or have you not looked at that yet?
So great. That's a really, really great question. And really what we've done, so my partner in crime in all this is Dr. France out of Ohio University, who is a very, very bright psychologist. And that's how we paired up on all of this. We are not, in our two trials, the safety trial was simply either you got the game or you got nothing. And it was a 3-day brief intervention just to make sure the game was safe. Right now, our intervention is larger, and it's a much, a 9-week intervention. But what we're comparing it to is dodgeball and sham dodgeball. And basically what we do is the computer already automatically, so the experimenters are blinded, the computer reads whatever their ID is coming into the study, and then they're randomly set into a control or experimental. The experimental group plays exactly as we've shown. It'll reach and have to bend. In the experimental group, all the targets are lifted up so that they don't have to bend to reach to do the game. So we're comparing movement to not having to move. We are not comparing it to standard of care, which is a really an interesting question and something that we didn't do. And actually, in some ways, it would have been much easier as I'm running this massive clinical trial where 230 subjects with 26 visits each coming into the lab, my postdocs are pulling their hair out. But our first step is to see what's the intervention, and what we hope to see at the end of this is that they have decreased pain and increased spine motion, decreased disability, and decreased fear. But that's what we're testing. And like I said, we're early in, we're about 100, well, we were 100 subjects in until COVID, and now we're just kind of rolling through it. But yeah, our next phase will probably do comparisons of cognitive behavior, like using a cognitive behavioral modules and no cognitive, so just a cognitive behavioral module, and then use a VR, the physical module, dodgeball, and then combination thereof. So those would be some other iterations of this moving forward.
Okay, thank you.
I have a question.
Yes.
My name is Azalea. I'm a radiation therapy student. I was just curious if you have had any patients that were like reluctant to get into treatment, or it didn't pique their interest, and if so, like how did you reach them to resonate the treatment?
Well, so that's a really interesting question. And one of the great challenges for anyone doing randomized clinical trials, they're really, really tough to do just to recruit people in. And there's, for good reason, there's layers and layers of rules. And so we have various physician groups. My study coordinator will go out and we'll have signs and to try to sign people up. But for coercion reasons, we really don't try to talk people into playing. We go through, so everyone does a pre-screen. So they have to have a certain level of characteristics that we need for the study. After their online pre-screening, if they meet that initial threshold, they come in, and then we do, I do, myself or two of the clinicians on my team do a physical exam. So, go through the history, look over what medications they're on, and then I do movement testing classically. And then if they meet the criteria based on all those and they don't have any other, so things that would rule them out of the study, hard neurologic signs. So motor weakness would be one thing that we wouldn't take them, or we think something else is going on. But the larger challenge right now, and I just ran into this yesterday, is a person came in, and PTs, will recognize this, with back pain, actually a former chiropractor who has a fairly significant left lateral shift. And as I went through the exam, clinical exam, he meets the criteria for all the criteria he meets to be enrolled in the study. As the PI in the study, I'm like, you meet the criteria. So, but before I signed him up, I actually went the opposite and talked to him about, as a clinician, I think, oh man, I would treat this doing X, Y, and Z. I don't know that dodgeball and I don't know that this is the right intervention for him. And I let him know. I said, you know, it may help. It may make you feel worse. So you need to be cognizant of that as you're coming into this study. That's like, I think the biggest challenge to me as a researcher, not trying to convince people to come in. That's a harder level. That's a lot of advertising. But when I see people as a clinician who they meet all the inclusion and exclusion criteria, they should be enrolled in the study. But as a clinician, my bias is I think I know what's wrong with them. But as a researcher, I'm asking the question, I don't know, maybe this is the right answer. So that's the larger challenge that I face right now.
Okay, thank you.
We have time for one more question.
I have a question.
Yes, fantastic.
So I know that you looked at spinal movement, but I had a question as far as like going off of what Vicky was asking. Have you noticed an association between movement strategies and individuals with high avoidance fear behaviors?
Yeah, it's interesting. So, so this data set is unlocked. So this is in data lock. I can't look at any of the data from the current RCT. But I have 3 postdoctoral fellows that are working for me, and you know they're at the point of the career they have to be just publishing. They're trying to make that next level to faculty. So I'm grabbing previous data sets that I have that we haven't published something on, and we're looking at like spine-hip ratios and how much they're moving, because some people have published the relationship between that and fear avoidance. So far, our data sets aren't really showing in terms of the spine-hip ratio, but clearly what we've seen in the past is that if they have high fear, they do tend to move the lumbar spine less. That's what we've shown repeatedly. On this particular data set, this is in lockdown, so we can't look at it for another 3 years. So, but that, you know, like I said, that's the nature of the beast.
Thank you.
Well, I think it might be time for us to move on. But my goodness, Dr. Thomas, thank you so much for an engaging presentation. We've all learned a great deal about movement and how we can apply this not only to our healthy older populations. I think you've given us a great deal to think about, and just an absolutely wonderful presentation.
Well, thank you very much. I greatly enjoyed being here. It was an honor to be invited. I would have loved to have been there in person. But like everyone said, everybody just stay healthy and we'll fight through the rest of this.
Thank you. Thank you very much. So I guess now we move on to the award section of our program. Take it away.
Thank you, Diane. Thank you, Diane. Hello, everyone. Greetings. I'm Paul Kilgore in the Department of Pharmacy Practice at the college, and ready to go forward. And I just want to ask Dean Lysak if you have any words before we begin. I realize she's muted, but I'm seeing a no.
Oh, I apologize, Paul. I was mesmerized by your very large fingers on the screen. You were asking if I had any remarks. I'm just going to second my enjoyment of the talk and let you announce the award winners, and then I will close. Thank you.
So as I believe everyone knows, year when we hold College Research Day, we receive a number of abstracts, and this year was no exception. There's a very large number submitted from across the college, a very, very impressive array. And if you haven't had a chance to look at the presentations and the information on the research presented done this past year, please take time to do that. And what I'll be announcing today are the award winners. All of the abstracts were carefully reviewed by the College Research Committee members. And we, of course, want to thank all of the College Research Committee members for their work and their time in reviewing these great presentations and this great research. So also, I wanted to mention that as we go forward today, you'll notice that there are first place and second place award winners. In the categories that you'll be hearing about, the first place award winners will receive a $500 award. The second place award winners will receive $250. And then the undergraduate award is an award of $250. So without further ado, let me start with the first category, and that is in the health sciences graduate programs. First place goes to Aaron Edwards. Aaron's abstract number is H06, and it's backward walking and dual task assessment, improve identification of gait impairment and fall risk in multiple sclerosis. Aaron, are you online now? Are you with us? Can you just say?
I am with you. Yes, thank you very much.
Great, great. Congratulations, congratulations. We're really glad you're here. Fantastic work. And we all look forward to taking another close look at your work and carry it forward, and look forward to more work in this regard. Thank you very much. Thank you. And of course, thanks to your co-authors and Dr. Fritz as well. In the second place for health sciences graduate programs, Joseph Toko has won second place from the Physician Assistant Studies program. His abstract is number H12, and his project is entitled Healthcare Experience Impact on First-Year Physician Assistant Students, Communication Self-Efficacy. And Joseph, are you with us today?
Yes, I am actually. Hello.
Congratulations. Wonderful. Thank you for being here. And we're really glad that you submitted the abstract, and look forward to seeing this out in print as well. And really great job on this work, and congratulations.
Thank you. Thank you so much.
Okay. And now we move over to the Pharmaceutical Sciences graduate program. In the graduate program for PharmSci, we have first place award winner Yao Fu with the abstract PSC 07. The title of project is Arsenic Inhibits the Tumor Suppressor-like Activity of Aryl Hydrocarbon Receptor in Epithelial Cells. And Yao has been working with a great team there, including Professor Chen. Yao, congratulations. Thank you for your submission, and we all look forward to taking a look at this really important project and the work you presented and submitted. So thank you very much for that submission. And moving ahead to our next category, second place Pharmaceutical Sciences graduate program, we have the project submitted by Majed Al-Harbi. Congratulations, Majed. Your project is titled Protein Ubiquinome of Primary Human Skeletal Muscle Cells Derived from Obese Insulin-Resistant Participants. Congratulations. This project is done with a collaborative team there, including supervision from Dr. Jinping Yi. But congratulations, Majed. Great job. Please, everyone, if you have a chance to take a look at the abstract number PSC 02, you get a few minutes. Great job, Majed. Thank you. Moving ahead now, we have in the PharmD candidate category for first place, we have Amina Amar. Amina's abstract is number PPR 03, and the title of the project is Pharmacist Impact on Physician Practices in Diabetes Management and Update. So congratulations, Amina. I believe Dr. Jaber is online, so congratulations to Amina and her team as well. Outstanding work, and so we really look forward to having everyone review your project online as well, and comments are welcome, of course. So thank you very much for that submission, Amina, and again, congratulations.
Thank you all, and to all your committee.
Oh, thank you. Hi, Dr. Jaber. Thank you. So now moving ahead to PharmD candidate's second place award goes to Regina Macedo. Regina's abstract is PPR 17, and the project is THC alters brain activation and improves efficacy of cognitive reappraisal in patients with PTSD, a neuropsychopharmacological approach to therapy. Regina, congratulations and great job on this presentation and submission. Thank you very much. Regina, are you there?
Yes, I'm here. Thank you so much.
Congratulations. Thank you very much. And And again, I encourage everyone to take a look at this great presentation poster online, and as well as all of the submissions, because we had a great number of submissions this year. So congratulations again. Moving ahead to our postdoctoral scholars program. In first place, the award winner is Yiling Xu. Congratulations, Yiling. Your abstract number PD03 is entitled Change in Frailty Status Predicts Fall Risks Among Older Mexican Americans. And supervision there with Dr. Fritz. And Yiling, are you there with us today?
Yes, I am. Thank you so much.
Congratulations. So glad you could make it today. And we really look forward to having everyone review and write comments and look carefully at your presentation online. So thank you again for this submission, and carry on this great work. Well done. Thank you.
Thank you. Thank you.
Okay, and moving forward to second place award for the postdoctoral scholars program, we have Taylor Morissette. Taylor is in pharmacy practice in the PharmD program, and the abstract number is PD05. Title of Taylor's project here is Preliminary Real-World Multi-Center Evaluation of the Clinical Effectiveness and Safety of omadacycline in patients treated for Mycobacterium abscessus. Congratulations on this project. Great work. We really appreciate you submitting it. And Taylor, are you here with us today?
Yes, sir, I'm here. Thank you all so much. Really appreciate it. Thank you.
Great, congratulations. Carry it forward, carry on, and well done. I look forward to having everyone take a careful look at your presentation today. Thank you.
Thank you.
Okay, moving forward now. In the undergraduate category, first place is Ryan Jones from the Pre-Occupational Therapy Program with abstract number UG01. The title of Ryan's project is Reducing Metabolic Syndrome and Unmet Needs Among Rural Breast Cancer Survivors during COVID-19, a feasibility pilot study. Congratulations, Ryan. Great job. Thank you for the submission, and thank you to Dr. Fritz as well. Ryan, are you here with us today?
Yes, I'm here. Thank you so much.
Congratulations. Glad you could be here with us today. We really appreciate your submission. Carry on this great work. You have a great future ahead, and actually, we wanted to thank all of the students, doctoral students, undergraduates, postdoctoral submissions. Congratulations to all of your hard work this year. It's really looking fantastic and incredibly impressive diversity and depth of research we have in the college. So before I move forward, I wanted to just point out one quick note for this year. Each year the college seeks to recognize senior faculty researchers who have established a distinguished record of contributions as a faculty member, but also depth in research over the past 5 years. This has the highest standards, including notable achievements through publications, grant making, and other key forms of significant recognition by the wider community. An executive committee reviewed nominations received this year from the Health Sciences Division, and this year a decision was made not to award the prestigious Senior Researcher Faculty Award for this year. However, we do expect there to be winners of the Senior Researcher Faculty Award in future years, so stay tuned. Of course, we'll carry this forward next year, and we expect to hear more in that category next year. Moving on to the next category is in the Junior Faculty Award category, and this year's winner is Dr. Jimei Wong. Congratulations, Dr. Wong, and we're so glad that we received the nomination, and we wanted to thank you for the work that you've been doing, the incredible contributions in research, and Dr. Wong's award this year will be in the amount of $3,500. And Dr. Wong, are you here with us today?
Yes. Hi, everyone. Thank you so much. I'm deeply honored to receive the award, and even furthermore, I'm very grateful that the college and the department has created such supportive environment for junior faculty in terms of career development and work-family balance. I'm very grateful.
Thank you, Dr. Wong. And I wondered, Dr. Wong, could you say just a few words about the research that you're doing in your laboratory and what directions you're taking it?
Well, I could talk on and on for an hour, but I'll take it short. My work is about how we can improve the tissue repair and regeneration in patients with diabetes. And what excites me about the work is that we have new technologies using gene therapy, stem cell therapy, and we have all the tissue engineering skills that enable us to help the patient to recover faster. We use animals, we work with the clinics to look at how humans react to all the therapeutic interventions that we propose. And hopefully we could find maybe one or two solutions to use in the clinic. And the other thing that I am doing is the hypertension research I started maybe a year ago. And we look at how salt-sensitive hypertension can be prevented or can be the blood pressure can be lowered by a new G protein coupled receptor. So it's a very basic research. But then I understand that we as clinicians or students, we may not get close to the basic science, to the small niche that fast. But I think that the good thing about doing science is that you maintain your curiosity about the science, about the world. And I think that maintain our use in the mind. So that's my thought, and hope you will enjoy science as I do, to all of you.
Fantastic. Thank you very much, Dr. Wong. Congratulations on your award. Keep doing this great work, incredibly important area. And again, thank you very much.
Thank you. Thank you for the committee for the award.
Okay, and I'll turn it back over to Dean Lysak. Thank you, Dean Lysak.
Paul, excellent job. Thank you very much for your warm enthusiasm and introductions of these amazing winners. And I think I need to steal Dr. Wang's words about passion, excitement, and scientific curiosity. I think we saw in our speaker today an enthusiasm, an energy for asking important questions. And whether we are at the bench with fluid and cells or all the way to people and communities, I think one of the most exciting things about the research in the college is its breadth and depth, but yet so focused on improving human health. So good on all of us. And one extra shout out to the crowd must be to the faculty who are supporting the students in this research as well. During these COVID times, we all have additional lifting that we're doing in terms of instruction and support of students, but I want to thank all of you who are senior mentors of junior investigators and student investigators to keep that energy and curiosity going. Thank you. I want to thank everyone as well for setting time aside today to join this Zoom Research Day. I think it worked out very, very well. Again, huge shout out to the research committee members for your leadership. And also, again, Michelle, Marissa, Tiffany, we couldn't do it without you. Congratulations one more time to all of our Research Day winners. Thank you to all. We will keep our fingers crossed that next year at this time, we'll be back down in the Commons looking at posters together. Until that time, stay well and have a great week. And this was truly fun. Thank you again for joining us and have a great day. Signing off.